Howdy everybody, welcome back to Urban Odyssey. Today we are going to do section 6 of the 6G white paper breakdown, this one on network automation. Alright guys, to get us started today, I'm going to go through a few new words, bits of terminology, that way you guys will have that before we start reading, and hopefully it will help you guys understand some things that you might have not understood had we not gone through the words first. So the first one is packets. Packets are kind of like the base structure of data that's sent over the internet. So I'll go ahead and read it. Packets. In the context of 6G network automation, packets are defined as data units that traverse the network and are utilized as active vessels for telemetry and control rather than just passive data carriers. They are characterized by the following functions. One is the encapsulation of metadata. Through in-band telemetry, packets are used to encapsulate metadata such as switch processing times, buffer occupancy levels, and policy rules within the data packets themselves as they traverse the network. Parsing and processing. Packets contain header fields that are extracted by a packet parser and processed by match action tables, which are within programmable data plane devices. And finally, state triggers. Malformed or specific packets can be used to trigger state transitions within stateful data planes, necessitating lightweight verification mechanisms to ensure integrity. A state is kind of like, at least in programming that I'm familiar with, a state is like, for instance, you might store a variable that has the user's account information in it that's logged in, and so the state would have access to information about the user. Next is network automation, the process of automating the configuration, management, testing, deployment, and operations of physical and virtual devices within a network. It aims to speed up service delivery and reduce errors by minimizing manual intervention. Self-driving networks, a network capable of measuring, analyzing, and controlling itself in an automated manner. It is defined as a network where measurements are task-driven and tightly integrated with control, using large-scale data analytics and machine learning models rather than closed-form protocols. Data plane programmability, a feature that allows data plane devices like switches to expose their packet processing logic to the control plane, allowing for complete reconfiguration. This includes modifying the packet parsing and processing pipeline and adding support for new protocols. Stateful data planes, a networking paradigm where stateful packet processing and control tasks are offloaded to data plane switches. These switches store packet metadata to provide context for processing new packets belonging to the same flow. P4, recognized as the programming language for the data plane, P4 supports various hardware, ASICs, CPUs, and allows the controller to specify packet parsers and match action tables. In-band telemetry, a method that uses programmable data planes to insert metadata into data packets as they traverse the network, providing high-quality network monitoring data without introducing additional overhead. Network slicing, the provisioning of differentiated services over the same physical infrastructure, In 6G, this moves beyond manual templates towards automated service decomposition. Network slice templates, NSTs, a definition file that explicitly outlines the virtual network functions and the associated service function chain required to comprise a network service. Intents, high-level goals, input into a self-driving network. They are categorized as one, imperative, explicitly details the steps a network must take, like shift traffic from balancer 2 to 3. And second, they're declarative, describes the end goal without specifying the method, such as minimize congestion. Quality of data, a metric emphasized in self-driving networks, where high-quality data is considered a prerequisite for achieving quality of service. And NWDAF and MDAS, those stand for Network Data Analytics Function, the control plane, and Management Data Analytics Service, the management plane. They're functions introduced in 3GPP releases to enhance data collection and analytics capabilities. All right. And that's all of the new terms. Those are going to be on the directory table that I put in the description. So if you would like to review those again, there will be a link in the description. This section 6 has a lot in common with section 4. So if you haven't seen section 4 yet, I highly encourage you to check those out. Let's see. There we go. Okay, let's get started. Section 6, Network Automation. SDN and NFV have been widely recognized as the major paradigm shifts that occurred with the advent of 5G. In particular, SDN has paved the way for the separation of the data and control planes, while NFV has been instrumental in decoupling the software from the hardware. Consequently, both wired and wireless networks have witnessed significant benefits from the adoption of SDN and NFV, including but not limited to simplified network management and service deployment, availability of advanced traffic engineering solutions and fine-grained network slicing techniques, and reduced CapEx and OpEx. A major contribution of network softwareization has also been the commoditization of key network components such as switches and base stations, allowing for their implementation on commercial off-the-shelf COTS hardware. In addition, the large open source community supporting these projects has played a pivotal role in engaging a wider set of stakeholders than was previously possible. As networks evolve further, the traditional network operations routine rooted in manual configuration and static script-based primitives cannot keep up with the increasing complexity. Instead, we posit that automation will serve as the major driving force behind building upon the improvements brought forth by SDN and NFV. And those, just so I can clarify, SDN, I believe, is server-driven networks, and NFV is network function virtualization. I think those are correct. More specifically, network automation is defined as the process of automating the configuration, management, testing, deployment, and operations of the physical and virtual devices within a network. Here, I will highlight that. Here we go. Network automation is intended to speed up the delivery of network services while adhering to dynamic and robust service level agreements, or SLAs, and reducing the potential for errors through minimization of manual intervention. Standardization efforts in this domain have led to the introduction of the Network Data Analytics function in the control plane and the Management Data Analytics Service in the management plane, which was the last two definitions that we looked at, for enhanced data collection and analytics functionalities. Within a 3GPP releases 15 and 16, Both these functions form a critical segment of the service-based architecture within 5G, highlighting the growing importance of network automation. To this end, we explore three key tenets of network automation in this section. Software-defined programmable data planes, automated service decomposition and orchestration, and self-driving networks. While the first two are primarily concerned with automating specific aspects of the network, i.e. the data plane and the network slicing procedure, self-driving networks are the holy grail, the holy grail of network automation, requiring absolutely no manual intervention. And so, yeah, this has to do with Section 4, programmable metasurfaces, environments, and a project known as Visor Surf in the EU is of key importance here. So I will put resources on the Substack post if you're interested in more information about that. Subsection A, software-defined programmable data planes. Being the most popular southbound API, OpenFlow is synonymous with SDN software delivery networks and has been featured widely in 5G networks. Yet, the stateless match action abstraction implemented by OpenFlow precludes true data plane programmability since it relies largely on static header field matching. Within the context of this paper, we define data plane programmability as a feature that allows data plane devices such as switches to expose their packet processing logic to the control plane in order for it to be completely reconfigured if required. Let's see. There we go. For example, the controller should be seamlessly able to modify the packet parsing and processing pipeline as required, add support for new protocols, and modify existing ones. To this end, P4 is being increasingly recognized as the programming language for the data plane. P4 supports a wide variety of hardware ranging from ASICs to commodity CPUs and allows the controller to specify 1. A packet parser for extracting header fields, and 2. A collection of match action tables that process these headers. Further, we note that the operation of many applications depends upon the real-time state of the system, and relying on the controller to update the forwarding state each time includes a significant latency burden. Consequently, there has been a growing body of research that seeks to develop stateful data planes, wherein some of the stateful packet processing and control tasks are offloaded to the data plane switches. For example, a stateful data plane device may store some form of packet metadata, using it to process new packets belonging to the same flow. The general packet forwarding rules are still set by the controller. However, the presence of state information provides context for rule selection at the switch level. Programmable stateful data planes present a variety of interrelated research challenges. First, there is need for a generic, broad-based definition of state, along with abstractions that expose this state. Second, since packet-level state maintenance will be done by distributed switching devices, there is a need for a state consistency mechanism. A mechanism of this kind could potentially be enforced through the controller to prevent conflicting forwarding actions. Third, security considerations present another important challenge. If the data plane switches are going to perform actions based on packet metadata, a malicious actor could easily use malformed packets to trigger state transitions, for example. In this case, ultra-lightweight mechanisms will be needed to verify packet integrity. Subsection B, Automated Service Decomposition and Orchestration. Network slicing allows for the provisioning of different or differentiated services over the same physical infrastructure and has been a major research focus in the cellular domain. Here's figure 6. I'll be able to put that up on the screen in a second. There is figure 6, and that shows you automated network slicing framework. However, the slice instantiation and deployment process is largely template driven and requires manual configuration. For example, current 3GPP network slicing specification is primarily based on the concept of network slice templates. An NST explicitly defines the virtual network functions and associated service function chain that comprise a network service. Consequently, such network slicing primitives allow for the deployment of a limited set of network services, i.e., only those services for which a template has already been defined. Clearly, an approach of this kind is not scalable because, one, it does not provide a mechanism to deal with new kinds of network services, and two, as network services increase in complexity, the effort required to create and maintain templates will become an operational burden. Going beyond the traditional template-driven model, we propose the concept of automated service decomposition and orchestration for network slice automation, as shown in figure 6. To this end, and in line with 3GPP terminology, we identify three major stakeholders. There's that word again, stakeholders. They like that a lot. See, the communication service customers, the communication service providers, and the virtual infrastructure service providers. There we go. The CSCs request communication services from CSPs who instantiate network slices and deploy them over infrastructure owned by VISPs to deliver the requested services. As part of the slice automation workflow, the CSCs provide high-level requirements such as those relating to latency, throughput, reliability, etc., along the lines of the emerging intent-based networking paradigm. Next, the CSC automatically decomposes the request into a constituent VNF forwarding graph, a VNF FG. It is important to note here that the service to VNF FG mapping is not based on a template, but instead makes use of deep learning models to extract service requirements and construct the corresponding VNF FG. The resulting service-specific VNF-FG forwarding graph also contains resource requirements for the constituent VNFs, allowing for seamless deployment onto the underlying infrastructure. Once the service has been deployed, continuous monitoring and real-time telemetry are used to ensure operational optimality. Subsection C, self-driving networks. For decades, the network operator has served as the centerpiece of network operations. However, the increasing complexity of communications networks, coupled with the constant state of flux brought forth by an ever-increasing number of connected devices, has made the task of real-time network management nearly impossible for human operators. Therefore, there is a strong case for transitioning from operator-driven networks to self-driving networks. More specifically, self-driving networks are expected to allow for elastic utilization of resources, error-free operation, prompt and targeted responses to security incidents, and provocative rather than reactive service handling. Seeking complete automation of network management, a self-driven network is defined as a network where 1. Network measurements are task-driven and tightly integrated with control of the network, and 2. Large-scale data analytics and machine learning models are used for network control as opposed to closed-form models of individual protocols. In a nutshell, self-driven networks should be capable of measuring, analyzing, and controlling themselves in an automated manner. At the outset, a self-driving network should take a high-level goal or intent as input. Expanding upon the concept of intents, we note that there are broadly two types of intents, imperative and declarative, which were in the definition we read at the beginning. While the former describes in explicit detail how a particular procedure should be carried out, the latter just describes the end goal without specifying how the stated goal should be achieved. For example, reduce network congestion by shifting incoming traffic originating at ingress node 1 from load balancer 2 to load balancer 3, which was the same one that was on the definition that I showed you. That's an imperative intent, since it explicitly defines the steps that network must undertake in order to relieve congestion. And on the other hand, optimized network operations is a declarative intent. However, a truly declarative intent of the kind described here would be extremely difficult to implement in the near future. Instead, semi-declarative intents that define more concrete goals would be far more helpful. Minimize network congestion is one example of such an intent, since it tasks the network with optimizing its operation by focusing on a specific objective, i.e., minimizing congestion. Based on the intent, the network is expected to determine 1. The measurements that need to be performed, 2. The corresponding inferences and learning that is required, and 3. The actions that must be undertaken in response to the input intent. And let me go ahead and show you the other figure real quick. That is figure 7, high-level architecture for self-driving networks. Okay, while a formal representation for self-driving networks is yet to be realized, remember this paper is 2020, a high-level architecture has been presented in figure 7, highlighting the importance of large-scale data acquisition, real-time analytics, and inference and programmable data planes. So the VisorSurf project that I told you about, that in my kind of way of analyzing it, looks like they have made some progress on some of these things. However, the realization of self-driving networks brings forth several research challenges as described next. The first is accurate intent definitions. As discussed previously, good intent definitions must toe the line between imperative and declarative If the intent is primarily imperative, it defeats the point of automation. On the other hand, if the intent is purely declarative, the automation procedure becomes unnecessarily complex. Therefore, there is a pressing need for formal guidelines that put forward a clear framework for intent definitions. For example, a framework of this kind could take into account customer expectations in terms of throughput and latency, network-wide resource optimization goals, along with other application-specific functions and services that are required from the network. 2. Automated real-time inference. Machine learning is vital to the automated decision-making process and self-driving networks. However, previous work in this domain has largely focused on applying pre-existing learning techniques for network control, which are not well suited for network data given its high volume, distributed nature, and rapid evolution. The major challenge here is the native integration of inference and control algorithms with the network's decision and control fabric. In addition, network design needs to evolve to improve the quality of data that is input to the designated control algorithms within the domain of self-driving networks. It is widely accepted that the quality of data is a prerequisite for quality of service. In-band telemetry. Research into in-band telemetry has been largely driven by the need for high-quality network monitoring data without introducing additional overhead. The INT approach makes use of programmable data planes to encapsulate additional metadata within the data packets themselves. Examples of such metadata include switch processing times, buffer occupancy levels, and even specific policy rules. As packets traverse the network, they keep accumulating additional metadata, which can be extracted as desired, thus providing highly detailed, accurate sets of network data. To this end, there is a need to quantify the impact of INT on network performance. In particular, metrics such as the relationship between the amount of metadata and packet size, the additional processing burden introduced, and the accuracy of the measurements obtained are all important parameters that merit careful consideration. So just before I end this, I just wanted to show everybody the page on meta surfaces that I set up so that people who want more information can check this out. It talks a little bit more about section 4 and shows you some images. That one's from figure 4, and some of these come from the VisorSurf project. And don't worry, when I finish reading through the whole paper, I'm going to do some work to summarize it all for you and for myself, because some of it is hard for the average person to understand, and that even includes me. Some of this stuff is very high level, and the way that the wording is used, in my opinion, is a bit underhanded, a bit kind of sneaky, if you will, because of all of the different acronyms and all of the different coded and soft language. So we're going to sum everything up at the end, but this is going to be a link that will be in the description in the post of the video. And also the table here, if you would like to look anything up, you can also click on the link. And so for instance, if you want to look up, let's see, telemetry, you can. In-band telemetry right there, packets right there. And I'm in the process of adding images to each of them, so this table will be updated frequently. You should bookmark it if you are interested in using it. Hopefully within the next couple months, this table will be very detailed, and so feel free to share it. It's free and it will remain so. And with that, guys, that wraps up section 6, and I will see you in the next video. Take care, guys.